Okay, so exam 3 is on Tuesday. (11-1). And so the deal is that, every semester I fiddle with things like oh, maybe it'd make more sense to do this order, change this or whatever. And so I changed the order of things a little bit, and it led to a lot of time before we could work on the new problems. And so the upshot is that the topics for this exam are exactly the same as the topics for the last exam. So 2D kinematics and all the stuff before that. Yeah. Yeah, we're not really behind. It's just there's just a big gap between when we started the new stuff and when we got to the point where we can do problems. Yep.
So for the labs, it's never accumulative, right?
The labs are, yeah.
They are?
Everything's cumulative. But I think in the labs I try to keep bringing up the same stuff, So so if you keep up with the labs, I think it makes you refresh the older stuff, All right, any questions about the test? Well, we're still talking about kinetics. We're getting to the point where you can work on problems in kinetics. One of the last things that we have to talk about is Newton's third law. Yes, exactly. Very good. Okay, so Newton's third law says for every action there's an equal and opposite reaction. Who's Newton? What's his first name? Yeah, so Isaac Newton, I can't remember. I think he was in the 1700s. Yeah, 1700s, definitely. But what?
Was it earlier than that?
I think it was 1700s. I'm 80-something% sure. What does it say?
Oh, I'll look it up.
I wasn't even looking that up. I'm just texting my mom. Equal and opposite reaction. Well, in the old days, way long ago, math papers and stuff like that they didn't use a lot of math symbols. It was all written out in words. It's really funny to read. So this is a sort of a paraphrase of what he actually wrote. This isn't the way that we're used to dealing with mathematical things, and so I'll try to put it into a form that makes more sense to us. But Isaac Newton was the most important physicist ever, and at one point he was working on some physics that there was no math suitable to solve the problems he needed, so he invented calculus. So he was amazing. Yeah, right. So the way to think about Newton's third law for us, anyways, a more useful form of Newton's third law says if you're dealing with a contact force between bodies A and B, So if you have a contact force between the bodies A and B, the force on A by B and the force on B by A have equal magnitudes and opposite directions. I think there's a lot of stuff that's counterintuitive about Newton's third law to most people when you first start thinking about it. In a lot of cases, it's really hard to imagine that two objects colliding with each other are applying the same force to each other. So let me, I'm going to bring up two kind of thought experiment sort of things, things you can think about that one of them I think will makes Newton's third law seem clear, and the other one is one where your intuition is sort of wrong about it, I think, most likely. So two cases of Newton's third law. The first one, this is the one where Newton's third law makes intuitive sense. Okay, so come with me on a mental journey. So imagine you're in this grass field, barefoot. Okay, can you feel the grass in your feet? Okay, and a soccer ball rolls over to you. You're just minding your own business, and then you notice a soccer ball's rolled over. And this kid goes, hey, kick this soccer ball back. And you look, and the kid's 10 yards away, like here to Emily, right over, So no problem, right? So you nudge the soccer ball back. You don't think about it. Okay, so now think about it again. So this time you're standing there barefoot on the grass, and the soccer ball rolls over, and the kid says, hey, kick that back to me. And you look, and the kid's all the way at the end of like a football field, 100 yards away, And you look down at your feet, you're barefoot, and it's not as appealing a thought to kick the ball back to him. Why is that? It'd hurt, and the reason it'd hurt is because in order to get the ball to go 100 yards, you have to apply a big force to the ball, right? I'm not trying to doubt anyone here, but you have to apply a big force to the ball. And if you apply a big force to the ball, if your foot applies a big force to the ball is going to apply, a force of the same magnitude to your foot. And that's going to hurt your foot if you're barefoot, And so in that sense, in that case, the idea of Newton's third law, I think, is pretty clear. We all have that experience of like trying to kick something with a bare foot, and the harder you kick it, you know that the more force is applied to your foot. So this first example is kicking a soccer ball. Kick a soccer ball barefoot. The harder you kick it, the more it hurts. And now, here's another example that it's a pretty similar idea, but I think this is one that's harder for people to wrap their head around. So this is the one where Newton's third law doesn't feel right, And so imagine a home run hitter a big 250-pound baseball player hitting a baseball 400 feet. So the baseball comes in, the bat applies a force to the ball, and the ball flies 400 feet. It's really hard to wrap your head around the idea that the ball and the bat are applying equal magnitude forces to each other, because it's very rare that contact is made and the ball stays there and the player goes flying away. It almost never happens. And so like, what's going on there? So a baseball hit 400 feet. Well, it really is the case that the force that the bat applies to the ball is exactly the same magnitude of force that the ball applies to the bat. You can measure it, and that's just the way it is. The reason that the ball goes flying and the player looks almost unaffected, the swing goes on as if the ball didn't hit. Well, there's two reasons. The first is mass. Remember that the force you apply to something is equal to the mass times the acceleration. So say that there's a 800 Newton force applied to the ball. Okay? That ball only weighs a couple of ounces. And so if you apply an 800 Newton force to something that weighs a couple of ounces, it makes it accelerate a lot. If you apply an 800 Newton force to a bat that's attached to a 250-pound man, there's not much acceleration. And then even more than that, another thing that adds to that effect is, so far that's what would happen if the baseball player was standing on ice. He'd hit the ball would go flying, he'd slip back a little bit on the ice because that 800 Newton force would make him accelerate a little bit, But the baseball player is also wearing spiked shoes that are dug into the ground. That's part of the earth, and the earth has a really big mass, And so even though those equal forces are applied to the ball and the player, they don't have nearly the same effect on the motion. And how many people here playing softball, like fast-pitch softball or baseball, ever swung at the ball and it was inside and it hit you in the hands? Okay. It's an unforgettable experience, and if you think of your hands as taking the place of the bat in that case, it's very easy to imagine that ball is applying quite a big force to the bat. You know what I mean? It applies a pretty memorable force to your hands when it hits you in the knuckles. Okay, so that's the idea of Newton's third law, and it's true of anything. Like, if I hit this paper, the force I applied, the paper just folds away, but whatever force I apply to the paper, it's applying in the opposite direction to my hand. It's just the way it is, and you just have to sort of little by little wrap your head around that. And I always draw this picture that when I took physics in high school for the first time, and we talked about Newton's third law, my physics teacher drew this really cool, hilarious picture, and I still just think it's like the funniest thing ever. So my physics teacher was probably 60, very overweight, very out of shape, very unathletic. And at the time, Mike Tyson was like making his way through the heavyweight division. I don't think he'd won a title yet, but he was like this fearsome young boxer, And my physics teacher was like, I wish they'd give me a chance to fight Mike Tyson. Everyone talks about how great he is. I wish they'd give me a chance. He's like, if I fought Mike Tyson, I guarantee I could hit him as hard as he hits me. And he drew this picture. So this is Mike Tyson's glove. This is his arm. I don't know. That's about what his arm looks like, I think. And then this is supposed to be my physics teacher's face. That's like sweat flying off, you know. And so let's think about free body diagrams of, like, what are the forces, the contact forces applied. Well, if you look at the glove, and you look at the face, the glove applies a force in this direction, a very big force, to the face. And Newton's third law says the face, therefore, applies a force with exactly the same magnitude, F. You know, that might be 10,000 newtons or something, some huge force, in the exact opposite direction. And so it's funny because it's undeniably true that if this happened, he would be hitting Mike Tyson exactly as hard as Mike Tyson hit him. It's just like the punchline of it is attacking a boxer's glove with your face is not an effective strategy, you know. Okay, so let's go through a few problems where I use Newton's third law, and you can see sort of how it comes together. Anybody have any questions yet? Okay, let's say that there are 3 carts rolling along the ground. So 1 kilogram cart touching a 2 kilogram cart, touching a 3 kilogram cart, and let's say there's a 25 Newton force applied to this side. And I'm going to use the usual coordinate system with the x-axis horizontal and the y-axis up. And what we want to figure out is, first, what's the acceleration vector? Notice that the motion is going to, these are going to stay in contact the whole time. So whatever the acceleration of this is, it's the same as the acceleration of that, same as that, and it's the same as the acceleration of the whole thing if we isolate the whole thing. And the second thing we want to figure out is the force vector on the 2 kilogram by the 3 kilogram. And I'm going to call this force vector on 2 by 3. Okay, so to find the acceleration, I think I mentioned before that when you have a bunch of bodies like this in contact, to find the acceleration, the first thing you do is isolate everything together. So free body diagram of the whole system. Okay, there's an outline. There's a weight force. What's the mass of the whole system? 6. Just add them all up. So 6 times 9.81 is the weight. That's 58.86 newtons down. And then the ground's pushing up on the system at the wheels. I'll just put it all in one place. And I'll call that the normal force. I'll call it the total. So we could break this up if we wanted into a normal force on the 1 and a normal force on the 2 and a normal force on the 3, but I just lumped them all into 1. And now we're going to go around the boundary looking for other places where there's contact. There's nothing on the right, nothing over the top. And the last thing that's touching the boundary is that applied force of 25 newtons on the left. And now we'll go to Newton's second law. The 25 Newton force is in the positive x direction. So that's 25, 0. N total is in the positive y direction. So that's 0 N total. The 58.86 is in the negative y direction. So 0, negative 58.86. And that's all equal to the mass of the system times the acceleration. What do we know about the acceleration of this system? We don't know the magnitude, and we don't even have to choose the direction, although it's going to be to the right because that's the direction of the force. But we do know that it's not going to jump into the air and it's not going to sink into the ground. So all the acceleration is horizontal. Okay? And that's okay. I have a solution. Yay! Okay, so I'm just going to write that as A0. And if it turned out that the acceleration is in, we know it's along the x-axis. If it turned out that it ended up being in the negative x direction, we just get a negative value for A and the math would work out on its own. Okay, so the x equation says 25 plus 0 is equal to 6a. And so a is equal to 4.16 repeating meters per second squared. And if we wanted to calculate anything about that normal force, we could do that using the y equation. I'm just going to leave that alone because it doesn't help us with anything we're asked for. Okay, so we have that from the first equation. But the problem didn't ask us for the value of that variable. It asked us for the acceleration vector. So to find the acceleration vector, notice that this is the acceleration vector. And so now we just take this variable value and plug it back into the vector that's in Newton's second law for the acceleration. So the acceleration vector is positive 4.16 repeating 0. And there's another way you can represent that vector as components, or you can just show it as an arrow in the right direction with a length of 4.16 repeating. So what direction would this arrow be pointing? It should be pointing to the right in the positive x direction. So you can also represent this like that. Any questions about finding the acceleration? Yeah, right. We could calculate the force that the ground applies to the cart, but we weren't asked for it, so I just didn't do it. Okay, so now part B, we want to figure out the force on the 2 kilogram by the 3 kilogram. When we isolate everything, the force on the 2 by the 3 is an internal force. We can't calculate it. So we're going to have to isolate one of the carts or some, subset of this whole system to figure out the force on the 2 by the 3. So what do you think for something to isolate? What should we isolate? So that's the most sensible first thing to think. If we're trying to find a force on the 2, then we want to isolate the 2. That's what Newton's law tells you, is the forces on the thing you isolate. But if we did that, we would have a force applied by the 1 pushing to the right, and a force applied by the 3 pushing to the left. We don't know what either of those two are. We only have one x equation from Newton's second law, so we wouldn't be able to solve for it. So instead, we're going to isolate the 3. We're going to calculate the force on the 3 by the 2. And then we'll use Newton's third law to give us the force on the 2 by the 3. Okay? So we're going to calculate that contact force between the 2 and the 3, and then use Newton's third law. We can't isolate the 2 kilogram because it's too many unknowns, too many variables. So instead, I'm going to isolate the 3 kilogram. So there's a weight force of 3 times 9.81. There's a pushing force from the ground. I'll call that N3. There's nothing in contact with the 3 kilogram cart on the right side or the top. But on the left side, there's a pushing contact from the 2. So I'll call that R for reaction. So Newton's second law says this R is in the positive x direction, so that force vector is R0. 29.43 is in the negative y direction, so that's 0, negative 29.43. N3 is in the positive y direction, and that's all equal to the mass, 3 kilograms, times the acceleration. Well, now we know the acceleration of the 3 kilogram cart. That's what we solved in part A. So this is, we can write this now as 4.160. Any questions about that setup? So the x equation says R plus 0 is equal to 3 times 4.16 repeating, which is 12.50. Well, that's repeating, so I think it's this, if you keep the 6's going forever. And so to calculate the force vector applied, so this vector in Newton's second law is the force vector on 3 by 2. And so force on 3 by 2 is equal to positive 12.50. But that's not what we were asked for. Let me give the other way you could do this. So that's 12.5 newtons in the positive x direction. So it's a vector that way. With a magnitude of 12.5. For Newton, yeah. So now, yeah, exactly. Now that what we want is the force on the 2 by the 3, we're just going to change the direction to opposite that. So, but what we wanted was the force vector on the 2 by the 3. So Newton's third law says the force on the 2 by the 3 is a vector in the opposite direction with a magnitude of 12.5 newtons. And if you wanted to write that in components, what would be the components of that? It's in the negative x direction. So it would be negative 12.50 newtons. Yeah. Any questions? So there's one thing that I want you to notice here. If you have this contact force written out as vector components, then if you're switching the subscripts, so if we're going from F32 to F23, that's just switching the order of those two subscripts. All you do is make each component the opposite of what it is. So we went from a vector of positive 12.50 to a vector of negative 12.50. Just switch the sign of the x component and switch the sign of the y component, and that has the same effect for Newton's second law. So I'm going to write that like this. The force on body A by body B is equal to negative force on body B by body A. You can think of that as an alternative form of Newton's third law. By the way, we actually could have done this problem without Newton's third law. So let me show you how to do that. By isolating the 1 kilogram and the 2 kilogram cart together. So free body diagram looks like this. That's the 1, that's the 2. The forces are a weight force. What's the mass of the system now? 3, yep. And 3 times 9.81 is 29.43. Then there's an upward force from the ground. I'll call that N1, 2, you know, the normal forces on carts 1 and 2. And now going around the boundary looking for contact, there's contact on the right side. That's a pushing force from the 3 kilogram cart. So I'll call that F, just give it a different name this time. And then when we get around to here, we have a force of 25 newtons. So Newton's second law. Well, anybody have any questions about that free body diagram? Does that make sense? So Newton's second law says that 25 Newton force is in the positive x direction. N12 is in the positive y direction. 29.43 is in the negative y direction. F is in the negative x direction. And that's all equal to the mass of our isolated system times the acceleration, which we know now. The x equation says 25 minus f is equal to 12.5. So 25 minus 12.5 is equal to f. So f is equal to 12.5. But now we want to make that into a vector. So what's the description of this vector? That's the force on what by what? That is the force on this 2 kilogram cart by the 3rd kilogram cart, the 3 kilogram cart. That's F on 2 by 3. And so F on 2 by 3, we're going to take this 12.5 variable value, plug it into that vector, and we end up with a vector negative 12.50, which is the same thing as a vector in the negative x direction with a magnitude of 12.5. So that should match what we got before. On 2 by 3, yes, negative 12.50. So can I point out something like weird about this? Look at what we isolated and look at what's included. When we isolated the 3 kilogram cart, there's no 25 newtons anywhere on here because it's not applied to the 3. And then we have this force applied to the right from the 2 kilogram cart. When we isolated the 2 together, now that 25 is there. It wasn't there in the other one. And now we have a force on the right going in the opposite direction. It's a totally different looking system. And yet somehow without, so think about when we isolated the 3 kilogram cart, that 25 wasn't in the picture at all, and yet somehow it's like it knew, you know? It knew somehow. It's like a ghost force. You know what I mean? Isn't that weird? So, anybody have any idea? Like, how does it know? Like, we didn't put that 25 anywhere in these equations. How did it know? Yes, exactly. It knew because of the acceleration. So in part A, we calculated the acceleration of the whole thing using that 25 Newton force. And then so when we used the acceleration from part A later on, it conveyed that information even though the 25 wasn't explicitly in that calculation anymore. Okay, let me give you a problem to work on. So let's say this is 5 kilograms, 10 kilograms, and there's a force of 50 newtons pushing to the left, and there's a force of 10 newtons pushing to the right. So first, what's the acceleration? And we want that expressed as a vector. And then second, what's the force vector on the 5 by the 10? And then third, what's the force vector on the 10 by the 5? Okay, so first let's just do part A. So take a few minutes, work together, ask me questions if you get stuck, calculate the acceleration vector, and then I'll go through it, make sure that you're on the right track with it, and then we'll move on to B and C. What I would recommend you do is just see how the steps you went through compare to what I do, and if there's anything where they, a place where they diverge from each other, then you know that's something that you need to try to understand better. Okay, so to get that acceleration, we'll isolate both of the two together. So there's a weight of 15 times 9.81. So 147.15. There's a pushing force from the ground. I'll call that N total. There's a 50 Newton force on the right and a 10 Newton force on the left. And so Newton's second law says 10, 0. N total is in the positive y direction, so that's 0 N total. 147.15 is in the negative y direction, so 0, negative 147.15. And the 50 is in the negative x direction. And that's all equal to the total mass times, we know the acceleration is horizontal, so I'll write that as A0. So the x equation says 10 minus 50 is equal to 15A. So A is equal to negative 8/3, I think. Which is 2.6 repeating.
You read the negative 2.6?
Yeah, negative, sorry. Thank you. Okay, and that is the value of the variable. To express it as a vector, remember that this is the form of the acceleration vector. So the total acceleration vector you get from plugging this variable value into this vector, and you get negative 2.6 repeating 0. And you can also write it as a vector in the negative x direction with a magnitude of 2.6 repeating. Does it make sense that the acceleration is to the left? Yeah, because the bigger force is pushing to the left. So that 50 Newton force is going to win over the 10 Newton force, and it's going to accelerate that way. This is sort of a funny thing about these problems. What direction do you think this is moving? Well, it's accelerating that way, but when we talk about the direction that something's moving, what we're talking about is the velocity direction. And remember that Newton's second law doesn't tell us anything about velocities. You know, velocity can be the same direction as acceleration. It can be the opposite direction as acceleration. We've seen that when we're trying to figure out whether something's speeding up or slowing down. So the answer is we can figure out accelerations, but without more information, we don't know anything about what direction it's moving. It's possible that this is going 50 miles an hour that way, and this acceleration is making it speed up. Or it's possible that it was at rest, and this is making it accelerate that way. Or it's possible that it's going 10 miles an hour this way, and that acceleration is making it slow down. We don't know anything about velocity without more information. Okay, so now take a few minutes and go through B, and C is pretty much instant once you get through B. So let me know if you have any questions. Okay, so part B, we're trying to figure out the force on the 5 by the 10. So I'm going to do a free body diagram of the 5. There's a weight force of 5 times 9.81, so 49.05. There's a pushing contact from the ground. I'll call that N5. There's the contact force applied by the 10 kilogram cart. This way, it's a pushing contact. Call that R. And then on the other side, there's the 10. So Newton's second law says this 10 is in the positive x, so 10, 0. 49.05 is in the negative y, so 0, negative 49.05. N5 is in the positive y. R is in the negative x. And all that's equal to the mass times the acceleration that we just came up with, negative 2.6 repeating 0. So the x equation says 10 minus r is equal to, what's 5 times 2.6 repeating? 13.3 repeating. Negative. And so R is equal to 23.3 repeating. And now we just have to take that value and plug it into this vector. This vector is the force on the 5 by the 10. So the force on the 5 by the 10 is equal to negative 23.3 repeating 0. That's in the negative x direction, so you can also write that like this. And then the last step, part C, says we want to calculate the force on the 10 by the 5. So that's just a Newton's third law thing. So the force on the 10 by the 5, we can do it two ways. First, we can just switch the signs of the components. So this is equal to positive 23.3 repeating 0. Or the second way we can do it is keep the value the same and just switch the direction. So it's to the right at 23.3 repeating. Any questions about that? That's enough, right? Okay. Okay, so test on Tuesday.